If you've written code that compiled, passed review, looked obvious, and still surprised you at runtime, this video is for you. Those bugs aren't syntax errors. They aren't logic errors either. They're expectation errors. You thought you knew what the code would do, so you stopped tracing execution and started trusting your mental model. The CPU never made that jump. Week 1 was about reading code in execution order. Week 2 is about something subtler, how your brain silently rewrites that execution while you're reading. Today we're going to break 4 pieces of code that fail only because your mental execution skips something the CPU never does. Literal execution is boring. One-line runs, state updates, that update is permanent. Mental execution is efficient and dangerous. It compresses steps. It infers intent. It skips anything that feels obvious. Most of the time, that shortcut works. The problem is that when it fails, nothing looks wrong. The code is correct. The logic is clean. Only your mental model is wrong. And you don't realize it yet. The failures we're about to see are not caused by bad code. They're caused by silent assumptions. Pause here and predict. Most developers read the comment and assume accumulation. They assume total keeps its previous value. Literal execution does not. The assignment replaces the value entirely. Previous state is erased. The bug isn't math. It's assumption. Your mental execution ran a different program. One where @item meant something that was never executed. This bug survives reviews because the intent feels obvious. Everyone agrees with the story. Execution never saw that story. Let's validate with the compiler. Recall that line 6, total equals 0. After line 6 execute, 0 value is completely gone. Let's run the program. Value of 54. We verified. The skip step here isn't arithmetic. It's state replacement. When your brain reads code symbolically instead of literally, it preserves old state that no longer exists. Execution never does that. Anytime you assume a value still matters, you must be able to point to the instruction that preserved it. If you can't, the value is gone, even if the code feels like it should still be there. That's how assumptions hide bugs. Most people compress this mentally. 5 times 2 minus 3. Now trace literally. After line 2, x is 10. After line 3, it's 7. Let's verify with the compiler. We're not going to walk through the code. We're just going to run the program. Let's run the program. Value 7. Verified. Now swap the lines. Same operations. Different state history. Different result. Let's verify this example with the compiler. Again, no code explanation. We run the program. Different value. Verified. Mental execution assumes commutativity. Execution never does. Mental execution collapses steps into expressions. Literal execution does not. Every assignment commits state. That state feeds the next instruction. If you skip intermediate states mentally, you are no longer reasoning about the running program. You're reasoning about algebra, and execution is not algebra. This failure isn't subtle. It's just invisible when you don't trace. Let's verify with the compiler. Again, no walkthrough. We run the program. Value 4. Verified. Most developers predict 3 iterations. Now trace. Start. I equals 0, gate open, run, I equals 2. Next I equals 2. Gate open, run, I equals 4. Next I equals 4. Gate closed. 2 iterations. The loop didn't stop early. Your mental execution skipped a state update. The loop stops when the gate closes, not when the work feels done. You assumed the loop advanced by 1. Execution advanced by 2. This is the cost of skipping steps. Loops don't think. They don't track intent. They recheck the gate using current state. If the state doesn't move the way you assume, execution won't either. This refactor looks harmless. Same logic, cleaner code, but execution changed. In the first version, B only runs if A greater than 0. In the second, short circuit rules decide. If B has side effects, timing just changed. The refactor preserved meaning, not execution. This failure is dangerous because it feels like progress. You cleaned up code before you fully understood it. Refactoring locked in a mental model that was already wrong. Tracing must come first. Refactoring before tracing doesn't simplify execution. It hides it. If you didn't trace it, you don't know it. If your explanation skips steps, it's wrong. Week 2 isn't about being slower. It's about being honest. Literal execution never skips. Mental execution always wants to. Your job is to stop it. These bugs hide because nothing looks broken. The code is correct. The logic is clean. Only the assumption was wrong. That's why experienced developers hit these bugs more often than beginners. Experience trains compression. Discipline preserves execution. That's the difference week 2 is teaching.